This lecture is going to be a quick note about how to think about current moving through resistors. To really understand this requires working through problems, but I want to have a quick description of what resistors in series means and what resistors in parallel means. Let's begin with resistors in series. So what you see here in the upper left are two resistors. I've labeled them RA and RB, and I want you to imagine current charges moving to the right. So they first move through resistor A and dissipate some energy, and then they move through resistor B and dissipate more energy. And you could imagine connecting resistors like this using your breadboards, for example. Um, now, it's a fundamental kind of rule, law, that when resistors are set up like this, current that moves through resistor A, like some sort of charges, they have nowhere to go. They can dissipate energy, but you can't dissipate charge. Like, you can't make the electrons disappear or the protons disappear. You can have energy leave the proton or the electron, but you can't have the electron literally disappear. So I represents literally the charges moving through, and because they can't disappear, the current, any charge that moves through RA must move through RB. So the diagram in the upper right shows what we're doing is exploiting that idea, saying any current moving through resistor A must also move through resistor B. Therefore, the current through resistor A equals the current through resistor B. So we'll call that, in this case, current through AB. That is the equation IA equals IB equals IAB. That is, all those currents are the same. And we can imagine treating these two separate resistors as a single resistor. And in this case, the rule is that you add up the individual resistances. So if the two resistors are, for example, 100 ohms and 200 ohms, then the combined resistance would be 300 ohms. Okay, so that's that's the beginning of our understanding of resistors in series. For resistors in parallel, it's a little more complicated. So these are the lower two diagrams. The idea here is that current reaches a junction and then splits, and any current chooses resistor A or resistor B, but not both, passes through that resistor and then joins up at a second junction. So you see those two blue circles represent the junction where the current breaks up and then where the current joins together. And in this case, the current may or may not be equal. The current might split up evenly, but it might not split up evenly. Generally, if the resistors are unequal, then the current will split up unequally. However, any charge moving through will have to have equal potential energy drops. That is, any charge that moves through resistor A will dissipate electric potential energy. Any current that moves through RB, resistor B, will also dissipate electric potential energy. And the way that they're set up, the energy they will dissipate will always be equal. It's a little harder to understand why this has to be true, but it does. It's kind of a metaphor for what's going on here is that if you have a river break up into two branches and then come back together, when they come back together, they have to join at the same height. You can't have one river join higher than the other river. That's kind of an imperfect metaphor, but whatever. So you can talk about the potential energy dissipated, or the potential difference across the first RA or across RB, but because of how they're connected, those potential differences will always be equal. And so you can represent that with equations by saying the potential difference across RA, delta VA, is equal to the potential difference across delta VB, and so you could also call that delta VAB. So that's the equation I've written for resistors in parallel have the same voltage difference. You can then you can treat RA and RB, you can kind of merge them together to get a combined resistance. And it's a little more complicated to kind of understand what it means to combine two resistors in parallel. But one consequence of that being more complicated is that the equation is more complicated. That is, resistors in parallel have that 1 over R plus 1 over R plus 1 over R rule for combining their resistance. Okay, so a second way of thinking about what's going on here is that for resistors in series, current moves through the first resistor and then it has to move through the second resistor. That, in a sense, is the definition of what resistors in series means. That any charge that passes through one resistor has no choice but to pass through the next resistor. If there is a choice, then those resistors are no longer in series. For resistors in parallel, it's a little more, the definition is a little more complicated. This is how I want you thinking about it. Current splits at a junction and then immediately moves through either the first or second resistor and then immediately combines at a second junction. If you have three resistors in parallel, then you can have the current split at a junction and immediately move either through the first, second, or third, and then immediately combine again at a second junction. So it is common for resistors to be neither in series nor in parallel. And in which case there's no simple equation for combining them. The general approach in circuits is to look for resistors that are in series and then combine them. Then look for more resistors that are either in series or in parallel and combine them. And typically through several steps you can combine all the resistors. You can't do it all in one step, but you can do it in several steps. Okay, we will discuss this in detail while doing problems.